Dear students, this video is prepared for the quick revision of the CAD subject. In the coming slides, whatever audio you are getting, that is generated using the text-to-speech software. Please go through it carefully.
CAD Approach to Finite Element Method. The basic idea is to find the solution of complicated problem by replacing it with simple one. Since the actual problem is replaced by simple one, we will be able to find only approximate solution rather than the exact solution. In FEM, actual body of matter like solid, liquid and gas is represented as an assembly of subdivision called finite elements. These elements are considered to be interconnected at specified joints called nodes. Step-by-step procedure of finite element method. Discretization of component. The first step in FEM is to divide the component/object/structure into subdivisions called elements. Hence the structure is to be modeled with suitable elements. The number, type, and size of the elements are to be decided. Selection of proper interpolation or displacement function. Actual variation of field variables like displacements, stress etc. inside the body is not known. We assume that variation of field variables inside the finite elements by a simple function called displacement function. In general, displacement functions are defined in terms of values of the field variables at nodes. Derivation of element stiffness matrices and load vectors. From the assumed displacement function, the stiffness matrix K, E, and load vector P, E, of the element E is to be derived using equilibrium equations. Assembly of element equations to obtain the overall equilibrium equations. The structure is composed of several finite elements. Hence the individual element stiffness matrices and load factors are to be assembled in a suitable manner, and the overall equilibrium equation are formulated as K equals P. WHERK is the assembled/global stiffness matrix. Is the vector of nodal displacements. P is the thank you for trying verbose. This recording will go away once the product has been purchased. Vector of nodal forces for the complete structure. Solution for unknown nodal displacements. The overall equilibrium equations have to be modified to account for the boundary conditions of the problem. After incorporating the boundary conditions, the equilibrium equations are solved for the nodal displacements. Computation of element stresses and strains. From the known nodal displacement, the element stresses and strains can be computed by using necessary equations of solid mechanics. Application of FEM for structural problems. Equilibrium steady-state time-independent problems, steady-state displacements and stresses. Eigenvalue problems, natural frequencies and buckling loads. Dynamic and transient problems, these are time-dependent problems. Facilities of CAD system in FEM. 1. Generation of mesh 2D or 3D structures. 2. Ability to represent curved edges and surfaces. 3. Ability to control element density and generation of non-uniform mesh. 4. Facility for concentrating on any region of the mesh. 5. Computational efficiency due to speed node and element numbering system. 6. Facility to display the discretization. Seven. Ability to rotate the discretization from any desired angle. 8. Option to display any portion of this model. 9. Input data can be modified for alternative idealization/discretizations. Application of CAD techniques to finite element data preparation. The input data for finite element analysis program consist of geometric idealization, material properties, real constants, and loading the boundary conditions. The major problem and a large proportion of the input is geometric representation of the structure by a suitable mesh. When this task is performed manually, it is time-consuming and subject to considerable errors. The human errors lead to abortive runs of the FEA program, which can be expensive. Automating the data preparation greatly enhances the use of FEM technique. General Finite Element Mesh Generating System, FEMGS. This system has two different modes of operations. 1. Automatic mesh generation. 2. Manual mesh generation. Automatic mesh generation. It is used for 2D and 3D components and structures. Mesh can be generated for a model using number of elements such as triangular with 3 nodes or quadrilateral with 4 nodes. The user may transfer the elements to higher order elements such as triangular with 6 nodes or quadrilateral with 8 nodes. The system can also automatically generate mesh for circular disks with or without holes using mesh of varying concentration. The GFEMGS system has a graphical checking system to check the coordinates and element connections so that any error in the data will be shown the user through display. Automatic node numbering and element numbering reduces the time for FEM data preparation. Manual meshing. Manual data preparation system makes extensive use of drafting. Each element is added to the model by using nodes through find subroutine and display system. Triangular mesh can be added by digitizing 2 fixed points using find subroutine, and third point of the triangle is identified by moving the cursor on the display. An element can be deleted by delete subroutine. User can identify the selected nodes on the display. Selected node are displayed in bright up form. Presentation of results. The results consist of nodal displacements, radial, axial, circumferential shear stresses. The results are displayed on the CRT display in graphical/numerical form. Graphic display of various stresses generated in standpipe of nuclear reactor is shown in following figures. The standpipe is subjected to internal gas pressure, outside is subjected to water jacket pressure and also axial loads from the supports. Dimensions. Loads. Meshing. Nodal displacements. Circumferential stress. Shear stress. Radial stress. Axial stress. (3D) shape description and mesh generation. There are 3 ways of entering 3D data into a computer. First method is based on digitizing 2/more orthographic views which are subsequently assembled within the computer to give the required 3D shape. The second method consists of digitizing contours in 2 dimensions with the third dimension normal to the surface and added numerically. A surface patch technique is used to interpolate the contour data to produce sufficient graphical representation. Third method is based on photogrammetry where 2/more photographs are digitized and data is converted into a 3D format. Out of these 3 methods of graphical representation, first method was found to be more suitable for complicated shapes. The method was varied slightly by dividing complex shape into a number of basic building blocks which are assembled at later stage. Input method for macro blocks. There are 6 different types of input shape designed to generate 4 different types of building blocks called macro blocks. Straight-edged block with uniform thickness, in this case only 5 input points are required to fully define the shape although there are 8 corners. Block with curved edges and uniform thickness, in this case, orthographic view of the structure will be taken such that the surface with the curved edge must be digitized in the XY plane. Only 9 points are necessary for fully defining the shape. Irregular block with straight edges. First case is special case of this, only difference is number of input points. 8 points are required for full definition of this shape. Irregular block with curved edges. 20. Input points are needed for complete definition of the shape. Solids of revolution with cross-section of straight sides. This input shape required 6 points. First 2 points for representing the axis of rotation. Last 4 points define the section to be resolved. Solids of revolution with cross-section of curved sides. 10. Input points are required for complete definition of the shape. First 2 represent the axis of revolution and next 8 points represent the section to be revolved. Discretization process. Basic elements. 1D/line element. If the geometry, material properties, and field variables of the problem is represented in one spatial coordinates, then 1D/line element is used. 2D element, when the configuration and other details of the problem are described in terms of 2 independent special coordinates, then 2D elements like triangle, rectangle, and quadrilateral are used. 3D element, if the geometry, material properties, and other parameters of the problem are described by 3 independent spatial coordinates, then idealize the body with 3D elements like tetrahedron, hexahedron, and rectangular prism. Size of the element. The size of the element influences the convergence of the solution. Hence it has to be chosen with care. If the size of the element is small, the final solution is expected to be more accurate, but using smallest elements leads to more computational time. Location of nodes. If the body has no abrupt change in geometry, material properties, and external loads, then the body can be divided into only one element. On the other hand, if there are any discontinuities in the problem, nodes are introduced at those discontinuities. Node 2 is introduced due to change in CSA. Node 2 is introduced due to variation in load. Node 2 is introduced due roller support. Introduction. CAD packages. Number of CAD softwares for modeling, simulation, analysis, drafting, synthesis, and optimization are available in the market. One can choose software according to their need and requirement. Solid modeling packages like Kasha, PROE, SolidWorks, Solid Edge, Unigraphics are used for creating geometric models. AutoCAD is widely used for drafting. Finite element analysis CAD packages are ANSI, NISA, and NASTRAN. FEA software comprises of 3 stages. 1. Pre-processing. 2. Processing. 3. Post-processing. Pre-processing stage consists of choosing the element, applying the material properties and real constants, creating the geometric model, and meshing. The processing stage consists of applying the boundary conditions, applying the loads, solving the problem. Post-processing deals with displaying the result, deflections, stresses and strains, etc. ANSI. ANSI is a well-established large-scale general-purpose FEA program. ANSI program has a comprehensive graphical user interface that gives easy interactive access to program functions. User can input data using mouse, keyboard, or combination of both. Modeling capabilities. Geometric structure may be defined through any of the 3 common coordinate systems: Cartesian, cylindrical, and spherical. It can be run in either interactive or batch mode. Element library. There are altogether 277 different types of elements that can be used to discretize a structure. The choice of element is largely dependent on geometry of the structure and nature of the analysis to be conducted. Pre-processing capabilities. Automatic mesh generation is available for complex 2D and 3D structural models. The user needs to define the geometry and boundaries of the structure. The input key points can create line segments to form 2D mesh on the basis of specified area discretization. 3D mesh on the basis of specified volume of mesh. Post-processing capabilities. Results of analysis can be printed/plotted in this module. Nodes, elements, keypoints, line segments, areas, volumes, boundary conditions, deformed shapes and solution data etc. can be obtained. Wireframe plots, shaded images and animations can be obtained. Program capabilities. Static structural analysis, it includes elastic, plastic, creep and backling stress analysis of small/large deformations. Dynamic structural analysis, it includes linear, nonlinear, transient vibration, model analysis and random vibrations. Heat transfer analysis, it handle both steady and transient heat flow in solids and heat transfer involving phase change and coupled thermal structural effects. Fluid dynamics and acoustic analysis, it includes potential flow, free convection, and mass transport. Kinematics analysis, it handles both rigid body and flexible linkages and mechanisms. Magnetic analysis, it includes inductance, flux density, flux lines, powerless. The main applications are solenoids, actuators, motors and transformers. Piezoelectric analysis, it handles problems involving 3D structure with AC/DC electrical sources such as transducers, oscillators, resonators, and microphones. NASTRAN. It is a structural analysis package developed in 1960 at NASA and widely used by the industry. NASTRAN is a large-scale general-purpose well-structured digital computer program. National Aeronautics and Space Administration have developed NASTRAN for structural analysis of aerospace industry. NASTRAN is famous for its capability to solve very large problems. It has the capability of identifying several identical components of a structure and arranges them symmetrical about an axis and to reduce the cost of computation. Program capabilities. Static and dynamic structural analysis. Heat transfer. Aeroelasticity. Acoustics. Electromagnetism. Buckling. Vibration. Eigenvalue analysis. Random response. Modules in NASTRAN. 1 message mesh, model generation program. 2 message stress, stress distribution model. 3 NAS plot, post-processing plotter program. NASTRAN library consists of various types of elements: 1D, 2D, 3D mass elements, damping elements, fluid elements, heat transfer elements, beam elements, shell elements etc. NISA. NISA is a large-scale general-purpose FEM program developed and marketed by Engineering Mechanics Research Corporation (EMRC). It has an interactive graphical interface called Display 3. Display 3 is a color graphics program for geometric and finite element modeling. This program is menu-driven and added with automatic mesh generation. The program verifies the model and directly creates the input file for various solvers. This software provides animation, shading, hidden line and boundary line plots with option for pan and zoom. Color plots of deformation, stresses, temperature, velocity, pressure etc. can be obtained. Program capabilities. NISA static, it is a linear and nonlinear static analysis solver. Material and geometric properties for linear and nonlinear problems are covered in this analysis. NISA dynamics, buckling analysis, transient analysis, dynamic response for random vibration, frequency response can be obtained in this module. NISA heat transfer, it is for steady state nonlinear transient heat transfer analysis. Thermal stress analysis can be performed. Endure, it is a fatigue and fracture analysis program. NISA Opt, this is a design optimization program. 3D fluid, it deals with incompressible and compressible fluid flow 2D/3D viscous, laminar, and turbulent flow problems. DIMES, this module is for simulation of vehicles, robot control, and mechanisms. EMAG, this module is for computing electrical and magnetic field distribution in electromagnetic devices. Auto Mesh, it creates a finite element model from purely geometric definitions of the boundary of the structure. Elements and nodes which are building blocks of the discretization model are created by meshing operation. Solver, NISA uses the wavefront technique to obtain the solution for equilibrium conditions which are in the form of simultaneous linear algebraic equations. It supports Cartesian cylindrical, spherical coordinate systems.